Hello, everyone, and welcome to today's D-Zone webinar, From Scanned Documents to Trusted Summaries, Building Auditable OCR to RAG Pipelines. I'm Max Crampton-Thomas with D-Zone, and I'll be your host. Before we begin, a few quick housekeeping notes. This session is being recorded and will be available on demand. You can submit questions anytime using the Q&A panel, and we'll address them at the end. Generative AI is accelerating document-heavy workflows across banking and other regulated industries. But when you combine OCR, retrieval systems, and large language models, new challenges emerge, from error propagation and hallucinations to governance, cost control, and regulatory scrutiny. I'm pleased to introduce our speaker, Lorenzo Balderrama, AI Solutions Engineer at Weights and Biases. Lorenzo works with engineering teams to build, evaluate, and monitor GenAI systems in real-world environments. Today, Lorenzo will walk us through how to design an end-to-end OCR-powered document summarization pipeline built for production, with a strong focus on observability, auditability, and model risk management. With that, Lorenzo, I'll hand it over to you.
Perfect. Hey everyone, as mentioned, we're walking through a pipeline that covers RAG, OCR, and observability. Throughout the demo, I'll be using tools like Weave, Pinecone, and Llama Index. But before I open any code, I want to talk about why this problem is deceptively hard. If you've ever followed a RAG tutorial, it usually starts with some nice clean markdown or a text file. That's not what real documents look like, especially in financial services. You're dealing with scanned PDFs, fax forms, sometimes literally a photo someone took of a bank statement on their phone. The traditional approach, using something like Tesseract or a classic OCR engine, returns a blob of text. From there, you're trying to apply rules or regex to parse it in a single string. And then you're manually trying to figure out which numeric value corresponds to which label. It's fragile and error-prone. What's actually changed, and this is the genuinely exciting part, is that multimodal models can now look at documents as an image and go straight into structured output. A lot of customers I've worked with have moved away from traditional OCR to this approach entirely. You skip the OCR step completely. It's not OCR then parse anymore. It's vision, extraction to schema. That's fundamentally a different way to think about document extraction. I wrote an article on this that I'll share at the end, but today we'll be walking through the pipeline I built around this approach. All right, let's get into the tools. We're using Weave for agentic observability. If you're not familiar with Weave, it gives us three key things: version control for your pipeline configuration, observability for debugging and identifying which tools your agent calls, and evaluations. So when you make changes to your agentic workflow, you can systematically determine whether things have improved or not. The great thing about Weave is that you can get started in 3 lines of code. The first thing is you're going to have to pip install Weave, import Weave, and then use a Weave op decorator anywhere you want to trace. That's all it really takes to get started, and we provide Python and TypeScript SDKs as well. We'll also be using Llama Index, but not as a traditional OCR replacement. It's more accurate to say we're using it as an extraction agent. Llama Index takes a fundamentally different approach. It parses the document while preserving layout and table structure. It extracts fields directly from your schema and returns them as typed output. No blob of text and no guesswork. I think this slide summarizes it pretty well, where we can see all the failure points and then how Llama Index can solve for that. I think the biggest thing that you'll see today is citation and reasoning hooks. These are great things because you can actually see where important values were extracted from and see the pages and use it as kind of a critical place for trust. All right, so let's take a look at the pipeline. So we'll start with scanned PDFs and images. That's the raw input. Those get put into Llama Index, which parses and extracts everything using vision. No traditional OCR. So what comes out is a clean structured data, like JSON or type fields. That structured text gets chunked with metadata, and that way we can preserve page references and citations. Those chunks get turned into embeddings, which are vectors that capture the semantic meaning of each chunk. And then it's inserted into Pinecone. That's the vector database we are using today. At query time, the retriever takes a user's question, embeds it, and then pulls the most relevant chunks using top K and filters. Those chunks become the context for the LLM. The output is a trusted answer with citations and extracted fields. And then if you notice around this whole pipeline, there's a little yellow dotted line. That's going to be Weave. Weave wraps the entire pipeline. Every step from extraction to retrieval to generation is traced and versioned. That's how we evaluate, debug, and iterate. Awesome. Let's go ahead and jump into the actual code. I won't be going line by line. I'll focus on key pieces from each file that contribute to the pipeline. I'll skip things like the boilerplate, like setting up a Pinecone index or iterating through uploaded files. And then after, I'll be sharing the repo, so you'll have the chance to run it, modify it, and build on top of it. The repo is actually broken up into a couple different folders. We have the Weave, RAG, Llama index, and the evaluation. Evaluation is technically part of Weave, but it's important enough that I wanted to stand on its own for the walkthrough. To run it, you're going to have to use this run, env.example to get started. You only need 4 APIs, and then you can specify it in index as well for Pinecone. But you'll just need Weave, OpenAI, Pinecone, and Llama Index Cloud API key. Awesome. When you use Llama Index, you're not wiring up an OCR engine. You're setting up an extraction agent. That's what the extractor.py is for. Let me go ahead and jump into that. Awesome. You'll notice we're also using Pydantic, specifically the base model. That's what we're importing. This isn't just for convenience. Pydantic has become the shared language of the Python AI ecosystem. OpenAI uses it for structured output. Llama Index uses it for extraction schemas. It's everywhere, and for good reason. Our schema is defined here in this income statement. And again, we're using that base model class. We get to see fields like company name, total revenue, cost of goods sold, all the way down to net profit. Each field has a description as well. And those descriptions are what the model actually reads to understand what to look for. If you wanted to extract a balance sheet instead, you'd have to swap in a different schema. The rest of the pipeline doesn't change. And then a little bit lower, you'll see the extract config. These 3 settings are doing a lot of the heavy lifting. We set use reasoning is going to be set to true. So the model knows, how to show its work, explaining where it found each value. The next in the line here is the site sources set to true. Essentially, it links every extracted field back to its source page. And then finally, the extraction mode is going to be the multimodal. This is what skips OCR entirely. The model reads the raw image directly. And that's really all it takes to get the extraction step. Instead of using a traditional OCR to parse and flow with regex and custom rules, we get reasoning, type schemas, and significantly more accurate extraction in one block of configuration. As I mentioned, the rest you can go ahead and dig through as I'm just setting up other information from Llama Index. All right. I'm going to go over now to the first part of our RAG system. We're going to go into the chunker.py. This is the part of the pipeline I want everyone to pay close attention to, because the chunking is probably the most underinvested part of the most RAG systems. I've seen teams spend a lot of weeks fine-tuning their prompts, days benchmarking their models, and then maybe like 15 minutes or so just using a chunking strategy. So for this chunker, we want to ensure that it doesn't produce bad chunks. So, if we do end up doing so, nothing downstream can really save you. Your embedding model is probably going to embed garbage. Your retriever retrieves noise. Your LLM reason over iterates and, gets irrelevant context. You can't really prompt your engineer out of bad chunks. Financial documents are semi-structured, so we need to be deliberate here. A naive strategy, like splitting every 500 characters, might put revenue numbers in one chunk and then label in another. That number is now meaningless without the context. All right, so in this file specifically, I've given you 3 different strategies. Again, they're just strategies. You have to decide what is best for the type of content you're working with. The first one is chunk text by line. So this one here, it's essentially a really simple approach where we split on new lines. It's really fast, but again, it's also naive because you could lose context between the lines. I'm going to skip this middle one for a second and then go down to the bottom one. This one is chunk by paragraph. Paragraph-aware splitting essentially respects the document structure. So if you have, different paragraphs, it'll split at those. But the chunk sizes become really unpredictable because not all paragraphs are the same. The one that we do end up using is going to be this chunk text with overlap. So this is one strategy you can utilize where essentially in the pipeline, it uses a fixed size window with with overlap. So no context falls through the cracks. It breaks at sentence boundaries, not midword. And then we use a sliding window approach where we move through the text in 500 character windows, but instead of cutting it off blindly at 500 characters, it looks back at the nearest sentence boundary. So we never split mid-sentence. Then it sets back 100 characters to create kind of an overlap between chunks. That overlap is critical. If a concept spans 2 chunks, the retriever still has a shot at finding it. So instead of having incomplete splits, we can now look and have more context when we're trying to retrieve. Awesome. I'll go ahead and jump over to the next one now. This is again the chunker. After chunking, we should probably embed these chunks into Pinecone. So the embed.py is where we do that. Here on line 16, we're using the text 3 small embeddings. A quick note for anyone who doesn't know what embeddings are. An embedding is a dense vector of floating point numbers. It essentially represents the semantic meaning of text in high dimensional space. When we embed a chunk, we convert it into a list of numbers, essentially becoming kind of the fingerprint for that text. This model outputs 1,500 dimensions, so every chunk becomes a list of around 1,500 float values. And every vector in our database must match that dimension. Otherwise, there's going to be a misalignment when you push embeddings to your actual vector database. If you wanted to switch to something like text embeddings 3 large that has roughly around 3,000 dimensions for better accuracy, you can do so. But it does come with 2 times the storage and the cost. So for financial services workloads, a smaller model might make more sense for you. And again, Weave is where you'd run those kind of comparisons so you can see empirically which one is better. All right, perfect. I'm going to jump over to the vector store. So we've chunked, we've embedded. Now we need a place to actually store this. Like I mentioned, we're using Pinecone. Pinecone is a managed vector database, so we don't have to worry about infrastructure, indexing, or scaling. It all kind of comes all in one. You don't necessarily need to use Pinecone. You can use others like MongoDB, Firebase, Supabase, or even a couple others out there. 2 things I do want to call out in this file is that inside the initialize index method, right here, we have a parameter we're defining, which is dimension. So as I said, the dimensions from your embedding model must be the exact to the actual vectors that you're embedding. So there's no mismatch. And this is kind of a common gotcha where I see people swapping out models, but not, correctly correcting in the vector base as well. You also see this metric cosine. This is essentially how similar things are between 2 vectors. Cosine similarity is the standard for text embeddings because it cares about the direction of the vector, not the magnitude. Pinecone also supports Euclidean and dot products, but cosine is what you want for normalized text embeddings. As I mentioned, again, there's some other information here for Pinecone, but the important piece is going to be this initialize index, so we can push everything to that store. All right. I'm going to go over to the retriever. So again, we've chunked, embedded, stored. Now we need a way to actually retrieve this information. The vector store handles storage and uses similarity search as well. So the retriever wraps the logic that you'd want in production. So things like query pre-processing, error handling, and even different retrieval strategies all exist in this file. In this one, I'm using one called pre-processing query. Essentially, it's a method that cleans up queries before embedding. It normalizes white space, it lower cases, and strips stop words like the, a, and, is for longer queries. The key detail here is that we only strip stop words if the query is longer than 5 words. Anything smaller than that, then we start losing the signal when we send it over. I have 2 strategies in here. The first one that I'm actually using is this retriever one, is this retrieve here. Essentially, it's a single stage retrieval. It pre-processes a query, it embeds it, in, and then it sends it up to Pinecone for top K for most similar vectors. And then it returns matches with scores and metadata. It's really fast, it's simple, and for most use cases, it's good enough. A little bit lower here, you'll also see this re-rank and retrieve and re-rank. This is a 2-stage retrieval. First, it overfetches with a large top K to cast a wider net. Then it passes those results to Pinecone's re-rank API across an encoder model. This essentially validates the query and the document together for a more accurate relevance score. It only returns the top 3 most relevant chunks from those 10 candidates, but the trade-off is latency and cost for precision. Right now, as I mentioned, we're using the basic retrieve method, but this is also something you'd want to use Weave for, so you can go ahead and swap between each 2 and then evaluate which one makes more sense for your use case. And then you can actually measure things like the re-ranking, answers downstream, and then start iterating on it a little bit more. I'll show an example later on of some of these evaluations we would produce in Weave, but for now, again, you can go ahead and play around with these 2, the retrieve and retrieve re-rank as well. All right, awesome. Cool. So that's all it really takes to get the RAG system set up. We've chunked, we've embedded, we've stored, and we can retrieve. And there's a couple different strategies you can play with. I'll move over now to the Weave section where we're going to go to the model.py. All right. This is a fairly large file because this is where we start to put things together. This file puts everything together in a way that you can go ahead and call all the different chunks in pieces that we've already completed in the other files. Weave captures that new version of your model every time you make changes. So let's say we want to change the chunk size, like here on this line 26. We can go ahead and update that, and it'll be a new version of model in Weave as well. All right, cool. All right, let me go a little bit further here, and we'll actually look at a function called load and process document. It's down here in line 58. This is essentially the ingest pipeline. It runs a full flow. It extracts structured data via llama index, converts it to text, chunks, embeds it, and then loads it into Pinecode all in one operation. The method that you probably want to look a little bit closer at as well is probably down here on line 211. Let me go a little bit further. Perfect. This predict one. This is the entry point for Weave. And this is what it uses to evaluate things. So it does two things. It retrieves context from the vector store, then passes the context plus the user query to the LLM. Because it's decorated with this weave op decorator, every call is traced. The query, the retrieve chunks, the generate answer all show up in the Weave dashboard. I'll actually jump over to Weave real quick to show you what that looks like. All right. So now that we're in Weave, we can go ahead and see the predict one. Top level is a predict function, as I mentioned, that we're capturing with the Weave op decorator. There's some parameters you can give it some different naming conventions so it doesn't look like just the word predict. Every step now is being collected, so we're seeing the inputs and the outputs. So if I click on this very top one, we see that we're actually entering information like the actual self-information of what was actually being retrieved. We can see the model. And this model is made up of a couple of different things. As I mentioned, we saw the index name, the space, the chunking, all that information we predefined in the model.py is going to be in here. And this is what we're versioning. So again, if we change something like the chunk size, this can become version 2 and then become a different model. So we can really easily see the input, what that was, and how that affects the output. And then the actual output. So we actually asked it to complete some kind of, evaluation. We've passed it some data sets, and now we can actually see those outputs as well. And we can see the retrieve context, understand a little bit why, and start debugging it even further. So let's say you actually got a step wrong. This is where you can come in, start looking at different hierarchy. Maybe we want to look at, the nested calls. All of that is possible, or even as some kind of graph view to understand maybe where we went wrong. All right. As I mentioned, in a RAG pipeline, you have a lot of moving pieces. When the final answer is wrong, it could be any of those steps. Without a trace, you're looking at an input and output and guessing what happened in between. With a trace, you open it up and see every step that's executed and in order, in the right order, and what is the inputs and outputs in that value. I'm going to jump back over to the code so we can look at the evaluation process. Again, I made this separate so we can understand a little bit deeper how do we evaluate this whole process. Maybe again changing system way to do the RAG, different prompt, anything like that. We can go ahead and evaluate. All right, let me go ahead and open up this Weave native evaluation. All right. Ideally, you would have some kind of pre-created data set. Either you can use synthetic data, or if you have historical data, which is better, you can go ahead and use that. That way you have, structured truths and understand what is a grounded truth when you're evaluating it and seeing those outputs from the model that you're testing. One type of evaluation that Weave provides is an offline evaluation. The idea is simple. You take the data set of questions, run the model against every single one, and score the outputs. It's not by hand. You define these scores and functions that I'll be covering here in a second. And then that's usually what measures what good means for your use case. And then Weave runs them automatically. There's two types of scores that we can build in Weave. The first one is a function-based score. It's deterministic, no LLM calls, just math and string matching. It's fast, cheap, and reproducible. Great for things like, did the numbers in the answer match the numbers in the context? And then the second approach is using an LLM as a judge, a model evaluating the output of another model. This one's a lot more powerful for things like subjective questions like, is this a helpful answer? Did we follow guidelines or compliance? Really, really great for financial documents where we have to stay in compliance for a lot of this information that we're using with AI. It does take a little bit more to set up, and it does come with a cost because you're using a second LLM. You could use the same LLM. Just be aware that there has been some research that says that using the same LLM might have some bias. So keep that in mind as well. All right. So for this pipeline, I'm sticking with the function-based scores because for financial documents, we only care about the metrics that are concrete and measurable. So we have 4 scores I've created here. We have this first one called recall at K. Of all the relevant chunks that exist, how many did we actually retrieve? If the answer lives in 3 chunks and we only retrieve 1, that's a recall of 0.33. This tells you if the retriever is casting a wide enough net. The next one is MRR at K. It stands for mean reciprocal rank. How high did the first relevant chunk rank? If the right chunk is result number 1, then the MRR is 1. If it's number 3, then the MRR is 0.33. This tells you if the best result is surfacing to the top. The next score that we have is numeric consistency. This is specific to financial documents. It checks whether the numbers in the generated answer actually appear in the retrieved context. If the LLM says the revenue is 15 million, but the number doesn't exist in the context, something went wrong. For financial services, this is going to be huge because that means we don't have hallucinated numbers. And in today's world, we've seen a couple of other organizations have this issue. So this is going to be really helpful if you're using for factual checking. And then again, with combination with Llama Index, you'll be able to retrieve and see that information step by step. All right, the last score I'm going to point out here is the simple faithfulness score. Essentially is the answer grounded in the context. It measures word overlap between the generated answer and the retrieved chunks with the bonus for matching numbers. A simple but effective proxy for did the LLM stick to what it was given or did it make up things? Again, another hallucination one and incredibly valuable and important for something like financial documents. Once we define these scores, we can actually move over to line 229 in this file. Let me go a little bit further. Perfect. This is a key piece. This is how we create an evaluation in Weave. It essentially wires all 4 scores into a single Weave evaluation object. This file uses an entry point that instantiates a RAG model with a specific configuration. It runs the evaluation and everything shows up in the Weave dashboard. Every query, every retrieval, every answer scored across all 4 metrics. The takeaway here is that evaluation isn't an afterthought, it's how we make decisions. So without these metrics, every change to our pipeline is just a guess. And essentially, we're just kind of vibe checking if it's correct or not. This adds real value because it gives you a systematic way to check this information. All right. So I've shown you how to essentially use Weave, Llama Index, and RAG all put together in evaluation as well. I now want to show you an example of all of this put together in a pipeline so we can see every step that we've created in these files into an actual producible demo. So this is the demo space that I wanted to showcase. And again, after you can go ahead and use it and kind of test and challenge it and change it if you need to. All right, so I'm going to actually upload a document here. All right, now we're going to go ahead and extract the data. All right, so now that we've uploaded the file and we've extracted the data, we can go ahead and see what was actually extracted. So in Llama Index, we defined a couple of things: the company name, total revenue, cost of goods, all the way to the net profit. It looks like we were able to extract that properly. And then underneath, remember how we did this configurations? This is the key thing, which was doing a lot of the heavy lifting. We can now see why each of these were extracted, and it gives you a reasoning and citation. So something like company name is going to be by verbatim, so it's a verbatim extraction. And then the citation on what page it was on, so page 1 of the sample organization. And then you can see that most of them were going to be verbatim extractions. Some of them will actually even give you further reasoning, like cost of goods. Use maybe like 60,000 in direct expenses, and that's the closest match it had. So you can go see the reasoning and the citation. And if this was incorrect, we can go ahead and modify the description a little bit more so we can get a more accurate extraction with Llama Index. All right, let me go further and continue. As I mentioned, we could see the chunks. Here are going to be the 2 chunks. It looks like we only got 242 characters though for that first chunk. We might have overdone it with the actual chunking of it. And then let's take a look at the vectors. So as I mentioned, these are going to be all the floats that we're sending to Pinecone. So you can go ahead and visually see that as well. And if we wanted to, we can go ahead and send it. That way, Pinecone has the most relevant and most recent information as well. All right, let me go ahead and hit continue. All right, now I can go ahead and ask it a question like, what is the net income? And did the organization perform better or worse than budget? Let me go ahead and run that question. In our files that we covered, this would essentially be used to be embedded, so we can go ahead and send it into Python as well. And that's what we did there. We went ahead and embedded it using the same model we use for the chunking strategy. All right. All right. After running the query, I want to point something out. And this ties directly back to what I was saying about chunking being the most underinvested part of the RAG pipeline. Let's look at the retrieval results. We pulled 5 chunks, but match 1 and 2 are nearly identical. Same company, same name, same total revenue. Essentially, the similarity score are also really low, around 0.47, which is not an ideally strong semantic match. Yeah, and then 4 and 5 just keep getting lower. All right, so I think this is what happened. Llama index extracts the structured data, which we convert to text, and the text is only about 300 characters. Our chunk size is 500. The entire document fits essentially in one chunk. So when we're asking Pinecone for 5 results, we're only really getting 1 or 2 meaningful chunks in the index. Matches 3 through 5 are essentially just noise. They're kind of irrelevant to this whole context, so we don't actually need them to be sending to the LLM for no good reason. This would actually make things very difficult, and we could potentially even hallucinate numbers if we did this. For a straightforward question like what's the net income, we probably still get the right answer, but that's because the signal is strong enough. But it's going to be harder on questions like this, where we're feeding the model almost, probably 60% of noise and asking it to over-reason. And as I mentioned, that's probably how we get hallucinated numbers. So for something like this, you'd want to adjust it. But here's the thing. I wouldn't have just caught this by reading the answer. The answer looks correct, but only when you look at retrieval steps that you see the pipeline is doing unnecessary work. That's why observability matters, and that's what Weave and other pieces of this pipeline give you. You don't just see question in and answer out. You see every step it took in between, and that's where the problems live. So if I was iterating on this right now, my next experiment would probably be dropping the top K from 5 to 2. Run the evaluation again and seeing if the faithfulness score improves because I've cut some of the noise out. And then I'd compare those next to each other in Weave as well, so we can see, did it actually improve? That way we're not guessing, we're not vibe checking, we're actually experimenting with this. All right. I do want to highlight what Weave looks like when we complete an evaluation. In this example, we'll be able to see what our scores are doing and kind of give you more insights into how evaluations work in Weave. All right. As I mentioned, this is going to be an example of the scores that we've created. We have the recall at K, MRR at K, numeric consistencies, and a couple others that I've kind of defined ahead of time as well. So we see those in the radar, in the bar plots actually, and we also get a radar plot. This compares 3 different models, and we actually get to see where things are improved. So we can see that maybe this model here is outperforming another. But to really get like a numeric sense of it, we'd want to check it below as well. So the only difference here is that we see is that the properties have different LLMs that we're utilizing. So GPT 3.5 Turbo versus GPT 4.0, and again, another GPT 4.0. These metrics down here are going to be the numeric values of those scores. So we can actually validate, instead of just reviewing the radar plot or just the bar plots, we can actually validate it using these numbers and seeing which one actually outperformed the other. So this baseline model looks like to be outperformed by the other 2 models that we have in here. And then you can turn off the diff only and see like what actually went into this. So everything that we versioned is essentially in here. All right. Let's actually take a closer look at the data set. As I mentioned, these are offline evaluations. So if I click on this first one, this is the first question in a row inside of a data set. We get to see the input. We actually ask it, what is the cash balance? And then we get to see step by step how it got to that answer, which is going to be here in the model output. And then we see the generated answer for each one. So for those 3 models, these are the generated answers. This makes sense because we're using 4.0 for both of these. And then again, Turbo maybe it is a little bit more accurate, but we'd actually be able to validate that using, the retrieve context, and then the actual raw matches as well. So that gives you all that information in here. And then if we ran this multiple times, we would see trials here and start validating. Maybe we did this for 5 times and see, okay, over, these 5 times, which model actually performed the best. Since everything's so non-deterministic, we would ideally want to see step by step, how did it get to that and if we're improving or not. Perfect. So as I mentioned, Weave gives you quite a bit of capabilities. I showed you traces and evaluations today. If we want to take it a step further, we could introduce things like monitors, playground for, evaluations that are not so committed with an evaluation step, or we can start versioning more of our assets. That's all I have for now, but feel free to play with it and sign up with Weave. And you'll be able to use a free account to start validating your own use cases. All right, awesome. Back to you.
Thank you, Lorenzo. That was a great walkthrough. We'll now move into audience Q&A. Please continue submitting your questions in the Q&A panel, and we'll get to as many as we can. For our first question, can I use any agent framework with Weave, like LangChain, Crew AI, etc.?
Yeah, so Weave has a lot of different frameworks that we work with. By default, we'll have some auto patching for a lot of these, but if we're missing some, OTel is always an option to be able to get started with Weave. But yeah, great question.
For the next question, how does Weave's trace graph handle multi-step agent workflows, and can we programmatically analyze trace trees to detect systematic failure patterns?
Yeah, absolutely. So as I showed in the traces, we're able to see step by step what our agent accomplished. If there's a step in there that, it did not necessarily do well or is incorrect, you're able to identify that. For things like multi-step or even multi-turn conversations, we have features as well that are included. So you can evaluate step by step what this agent did. Is it correct? Are we moving towards the right answer? And then get a hierarchy view that encapsulates all that.
Another audience member asked, can I access this code in GitHub?
Yeah. So, as I mentioned at the very beginning, this is based off of an article that I created. The article will be shared afterwards as well. And then the repo will also be available to all of you. So you can go ahead and clone it, change it, and make it a little bit more closer to your own use cases.
Perfect. And I think we have time for about one more. Can I try this out for free? And what's included in a free account?
Yeah. So this is all able to be started for free. We give you about, I want to say a gigabyte or so of free usage. But essentially, you don't really need anything to get started. You can go ahead and go over to W&B.ai, start checking out some of the other products as well. But Weave is totally free to start.
Thank you again, Lorenzo, for sharing such a thoughtful approach to building trusted Gen AI systems in regulated environments. It's clear that accuracy and compliance can't be afterthoughts when teams combine OCR, retrieval, and large language models. Observability and auditability must be built in from day one to make these systems truly production ready. Lorenzo, before we close, I'd love to hand it back to you to share how attendees can continue the conversation and learn more.
Yeah, no worries. Well, as I mentioned, the articles are here. There's some nice QR codes that you can scan to be able to capture this. You can also schedule a demo to get a closer look at your use case. And then again, you can go ahead and clone the repo. So feel free to reach out to do so. And then I will actually provide also the socials so you can go ahead and connect with me on LinkedIn and then ask me any further questions you may have.
Thank you, Lorenzo, and thank you to everyone who joined us today. Keep an eye on your inbox for the on-demand recording, and we hope to see you all at a future D-Zone webinar. Thanks again, everyone.